जॉईन झाले का म्हणून विचारताय तुम्ही व्हिडिओ सुरू करा.
हा व्हिडिओ
पॉज करून ठेवतो. करून ठेवलं तू. नाही थांब.
असं करायचं तुम्हाला शेअर करतो ना व्हिडिओ
शेअर साऊंड. बरं ठीक आहे मग कॅन्सल. हे होत आहे ना. ही लिंक आहे तर ही टाकायची.
Now it is streaming live on YouTube also, sir.
Yes. So please copy the link and put it in our Telegram group.
Actually, I have not got link. Actually, I have got notification on the Zoom meeting.
Just I'll do it.
Okay. Please share it on Telegram group also, sir.
And now we can allow participants to join.
Okay, sir. I am allowing all the participants to admit.
Everyone publicly.
Yes, sir.
डुगो हे आणून दे. मामाला हेडफोन लागत नसेल तर मला आणून दे.
मग बघू पण ते पण करू शकतील ना योगेश आणि झाले जॉईन. युट्यूबला ऑन झालं. वेटिंग झूम
दिसायला लागलं. तुम्ही कंटिन्यू करा. तुम्ही लाईव्ह
येस
एकदा लाईव्ह दिसतो.
काय दिसतं अजून काय याच्यात
काहीच काही साईड पॅनल वेटिंग ऑफ केली आता जे डायरेक्टली ऍड.
बरोबर.
All set, sir?
हो रहा just 1 minute.
Yes. Just 1 minute.
Thank you, sir. कुठे आहे हे होस्ट का co-host
Host करा.
आणि कळशे सरांना केलं co-host तू?
नाही.
कर ना मग कळशे सरांना. मी करतो.
तुम्हाला करावं लागेल सर. कळसे सर, त्याच्यानंतर लोहार सर, रामानुजम सर आणि किलानी सर
ऑलरेडी आहेत. लोहार सर ऑलरेडी आहेत. आणि एक मिनिट पळणी सर.
कळसे सर पण कोर्स आहेत.
आय विल मेक हिम ऑल्सो.
ओके.
अरे यार ये क्या आ रहा है? एक मिनट मिलिंद. नहीं गया. पण पोस्ट करतो.
पलानी सर झाले.
Yes. So everybody is in the main stream now.
Sir,
Should we start?
No, sir. Wait for a minute. I think Ramanujam sir is not co-host now.
I'll make him co-host.
And also make co-host to Dr. R.M. Sodhi sir, or head of the department.
Kela already.
He is not a co-host. Okay, sir.
Co-host. Okay. Participants भी join हो गए हैं.
Yes, sir. 83 participants are on Zoom.
Okay.
And think.
Okay, so very good morning to all the participants faculty members, and researchers. Today we are here for the microscopy, national level microscopy workshop. Am I audible?
Yes, you are.
Yes.
Okay, thank you. So I welcome all the participants and faculty and delegates and students to this national level workshop on microscopy, which is organized by Department of Zoology and hosted by Eco. Just wait. नहीं इको आ रहा है इको एक मिनट
Carry on, sir.
You continue, sir.
ओके सो इको आ रहा है इको
Sir, it is actually to your side only.
ना रिपीट हो रहा है वो
We are not getting the echo.
just हाँ okay so now it's okay because it was on YouTube. On behalf of PSGB Mandal SI Patil Arts, GB Patel Science and STKVS Commerce College Shada, I welcome all of the participants and today we have our delegates, our honorable principal, Professor Dr. R.S. Patil sir. We have with us today's distinguished speakers, Dr. Saravanan and Dr. Palni. I welcome them. Also, we have with us our vice principal, Dr. M.K. Patil sir. I welcome him also. And our head of the department, Dr. R.M. Chaudhary. Okay. I request Professor Dr. R.S. Patil sir to be the president of this event. Hello. It is my kind request to Professor Dr. R.S. Patil sir to be a president of this event. Okay, thank you, sir. Today is a very auspicious day of Guru Purnima, and on this occasion, I would say, Gurur Brahma, Gurur Vishnu, Gurur Devo Maheshwara, Gurur Sakshat Parat Brahma, Tasmai Shri Guruve Namah. Our Indian tradition is to worship Guru and to worship Goddess of knowledge, Saraswati. I would play Saraswati Vandana to inaugurate this function on behalf of all the delegates, all the faculty members, and all the students.
या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्करप्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा शुक्लां ब्रह्मविचारसारपरमा आद्यां जगद्व्यापिनीं वीणापुस्तकधारिणीम् अभयदां जाड्या हस्ते स्फाटिकमालिकां विदधतीं पद्मासने संस्थितां वन्दे तां परमेश्वरीं भगवतीं बुद्धिप्रदां शारदाम्।
Now I request our Vice Principal and Chairman IQAP, Dr. M.K. Patil sir, to please introduce our institution.
Thank you, Dr. Bhande. Good morning, ladies and gentlemen, and my dear colleagues. It is my great pleasure to welcome you all to the inaugural ceremony of the virtual national level workshop on microscopy organized by Department of Zoology, Pujya Sane Guruji Vidya Prasarak Mandal's Art Science and Commerce College Shahada, which is affiliated to Kavayatri Bahinabai Chaudhary, North Maharashtra University, Jalgaon, Maharashtra. Today's inaugurator, Dr. Ramanujan Srinivasan from NISCR Bhubaneswar, Dr. Sarvanan Palani, ISC Bangalore, chairperson of this workshop, our honorable principal, Professor Dr. R.S. Patil sir, distinguished guests who have joined this workshop from affiliated university as well as from other states also, Dr. R.M. Chaudhary, our head of Department of Zoology, Dr. S.R. Bhande, convener of this workshop, Dr. Y.H. Vasu, organizing secretary, all the organizing committee members, faculty members of Zoology Department, research scholars, and my dear students. It was the dream of our beloved founder president, late Anna Sahib P.K. Patil, to provide education to all levels of the student community, along with the creating a feeling of bonding and commitment among the academic and non-academic employees. The ethos of our Mandal is marked by the patriotic fervor, selfless service, and a spirit of indigenous enterprise. These values permeate all the institutions set up by the Mandal and are the guiding principles for all of them. After beginning its journey in 1970s, PSGVPM has blossomed into an educational colossus that has attained recognition in multiple streams of higher education. We have mastered the art of being able to transform itself into a close-knit family and at the same time help its students to attain all-round development, be employable, and achieve success. Sir, our Mandal has now grown into an educational foundation, promoting global thinking consistent with the national interest and promoting the values, professionalism, social sensitivity, and dynamic entrepreneurship. We provide education from KG to PhD, and nearly 2,500 plus students and 70 faculty members are working to extract the best part of education. Our college has a honor of college with potential for excellence. Similarly, we were accredited in the third cycle by NAC in 2017, and we have attained A grade. Recently, in the last 2 years, we have received grants from RUSA for component 9 infrastructure grants for colleges of rupees 2 crores, and we are recognized as a DBT star institution. Recently, we have also received the vocational courses, BO courses by the NSQF. So, with the motives in our hand, and recently we have completed our golden jubilee year of the institution. Friends, we are aware that the whole world is facing the COVID-19 crisis, and all the teachers, they are trying their level best to reach out to students by adopting every means of learning activities. We are facing the fourth cycle next year. So we have been organizing a variety of programs related to academics, co-curricular and extracurricular throughout the year. Our management and our principal always motivates us to organize such events. Students of this college continue to bag top positions in the merit list, retaining the status of the college among the premier colleges. Every year, 8 to 10 students they bag the medals in UG and PG courses. There are different reputed recruiters for campus placement, such as Bharat Ambuja, Bharat Fertilizers, Saffron Technology, Mankind Pharma, Mahindra Finance, ICICI, HDFC Bank, and so on. So, considering the long-term goals of the institute, it is our firm belief that the research activities also have to be given a major thrust, and all the efforts are being made to enhance the same. Scientific growth has also been fueled in the college with new improved facilities for research and laboratory training. Moreover, on account of the college's initiative, there is an appreciable increase in the number of publications of the faculty. Research scholars, they are recipients of Inspire Fellowship, CSIR SRF, HG Raisoni Doctoral Scholarship, UGC CSIR GRF, and so on. So our college is constantly encouraging our faculty and students to develop a system for conscious, consistent, and catalytic action to improve the academic and administrative performance of the institution. We promote quality related issues through various activities such as seminars, workshops, conferences, panel discussions, academic meetings for all the stakeholders of our institution. Our zoology department is a thriving community of dedicated teachers, diligent researchers, and devoted students, which shares the enthusiasm for the subject. The department offers graduate, postgraduate, certificate courses, and PhD programs. The faculty members are also actively engaged in carrying out research and projects. Students of zoology, they are provided with ample opportunities to provide the organization skill and group dynamics. They are motivated to handle seminars and participate in group discussions. In this process, today we have with us a pool of distinguished and learned guest speakers, Dr. Ramanujan Srinivasan and Dr. Sarvanan Palani. These dignitaries have been very much instrumental in their field of life sciences and have been key persons in various conferences as a resource person at national level. In this workshop, we will be providing a valuable opportunity for the students and educationalists to share their experiences. I am grateful to the experts and the guests who have joined from the colleges nearby our university, as well as from the state, as well as out of the states. And I think that it will be helpful to bring these experts and they can realize that together the potential of technology for scientific community. I would like to conclude my talk by encouraging the delegates to participate in all activities and discussions. I wish everyone a successful, safe, and fruitful workshop by looking forward to the learning about the outcomes. Thank you.
Thank you so much.
Uh,
Monday, sir.
From National Institute of Science, Education and Research, Bhubaneswar. And another speaker, Dr. Sarvanan Palani, is from IISc Bangalore. Now I would like to request Dr. Ramanujam sir to please deliver inaugural talk for this event. Dr. Ramanujam sir.
Good morning, everybody, and I hope I'm audible.
Yes, you are audible, sir.
Thank you. So, first, take the opportunity to thank Dr. Bande for this wonderful opportunity for me to just talk with the students at your esteemed institute, and also a wonderful introduction from Dr. Patel on what the ethos of the college and the Department of Zoology is, and why this conference or the workshop on microscopy is organized and what they would like to deliver to the students. So it's kind of really wonderful to see so many student participants even at this times joining with their whatever devices they have in hand, and most of us have some small devices. And this one, it's great to see all of you, and thank you all of you for this wonderful opportunity for me also to share what our experience or what we can reach out to the students and try to be useful as a scientific community to the students and bring out our philosophies and tell them what we are and what research is all about. So given that, I think the speakers today, one of course is myself, and then Dr. Saravanan Palni, I'm sure will take you through this wonderful landscape of what we see through microscope and why this microscope or why seeing things has been absolutely essential for the human experience when in what we understand around the physical world. So I think in that process, microscope has played one of the most fundamental principal roles, because as humans, our eyesight is the most important thing for us, and we would love to see things and we engage with things, and that is where we gain our experience and understand things very closely, and we base our philosophies and our ideas, everything over what we see. So in that sense, microscopy is not just looking research and science, but it's a part and parcel of our entire life and ideas and philosophies that we form around. So I think it's going to be a great talks here, and students should learn a lot of things, and look forward to the interaction and questions from the students. And that I'd really like to again thank Dr. Patel and Principal Patil and the head of the department, Dr. Professor Chaudhary, and all this for organizing all this and having both of us in this meeting. Thank you so much for that. I would like to end the. Thank you.
Thank you so much, Dr. Ramanujam, sir. Now I would like to request our beloved Principal Professor Dr. R.S. Patil, sir, to please deliver presidential speech.
Thank you, Dr. Bhande. Good morning, one and all. First of all, wish you all happy Guru Purnima. Students of this national workshop, Honorable Bapu Sahib Deepak Bhai Patil, President of Pujya Sahib Guruji Vidya Prasarak Mandal Shahada, Honorable Kamal Sahib Patil, Secretary Pujya Sahib Guruji Vidya Prasarak Mandal Shahada, Honorable Sri M.N. Patil Sir, Coordinator of Pujya Sahib Guruji Vidya Prasarak Mandal Shahada, Inaugurator of National Workshop, and we have been listening to the learned person, Honorable Dr. Ramanujam Srinivasan, IISc Bhubaneswar, Research Person, Honorable Dr. Saravanan Pillai, Professor P.S. Lohar, Chairman of Board of Studies in Zoology of Kavitri Bahinabai Chaudhary North Maharashtra University, Jalgaon, that is our affiliating university. Professor A.T. Kalse from Rashtriya College, Chalisgaon, dignitaries online, Vice Principal and IQAC Coordinator, Dr. M.K. Patel, Dr. S.D. Sinkadkar, DBT Coordinator, Professor R.J. Syed, Head of our Zoology Department, Dr. R.M. Chaudhary, Convener of this workshop, Dr. S.S. Bhande, Organizing Secretary, Dr. Y.H. Vasu, Professor Ms. Sarika Fulpagare, professors and students, greetings of the day. Hope you are doing well in this pandemic caused by COVID-19. Friends, as we know that COVID-19 is a public health emergency of international concern, who declared COVID-19 as a global pandemic on 11th of March last year. Global researchers are working around the clock to find the treatment on this particular COVID-19 and save the lives and they have developed vaccine for the future prevention. India's proactive, preventive and productive approach to fight COVID-19 pandemic started under the eminent leadership of our Honorable Prime Minister Sri Narendra Modi. We are fighting against this pandemic in Maharashtra under the able leadership of Professor Honorable Sri Uddhavji Thackeray, Chief Minister of Maharashtra. Friends, I take this opportunity to introduce my college, my institute in brief. 50 years ago, a renowned personality, freedom fighter, Sahkar Maharshi and foresighter visionary, late Sri Anna Sahib P.K. Patil, initiated noble cause of education in the form of Pujya Sahib Guruji Vidya Prasarak Mandal Shahada. Pujya Sahib Guruji Vidya Prasarak Mandal, S.I. Patel Arts, G.B. Patel Science and STKVS Commerce College, Shahada laid its foundation stone in 1970. The college has a progressive management team led by Honorable Bapu Sahib Deepak Bhai Patil, President of Pujya Sani Guruji Vidyaprasad Mandal Shahada. In addition to the star college status, as said by our Vice Principal and RUSA Beneficiary College, we have been accredited by NAC Bangalore just a couple of years ago and received A grade with a CGPA 3.12 in July 2017. Proud we feel to mention our position as an A grade college as ranked by the affiliating university, that is Kavitri Bahinabai Chaudhary North Maharashtra University Jalgaon, consecutively for 5 years. Educational history for more than 5 decades and the healthy tradition of the college attract students not only from this Khandesh region of Maharashtra but also by nearby states just like Madhya Pradesh and that of the Gujarat. The facility comprises of more than 60 learned members, that is faculty members and experts in their own subjects, offering their valuable services with sense of dedication and devotion. The college, after laying its stepping stone in 1970, received the recognition from UGC under 2F and 12B, and ours is a permanently affiliated college to the affiliating university, that is a KBC and UV Jalgaon. With the introduction of graduation courses in basic subjects, we have now reached the present status wherein 16 courses are offered at undergraduate level and 13 courses are offered at postgraduate levels. Our 11 departments are recognized research center by the affiliating university. The emphasizing aspect worth mentioning is the facility of acquiring PhD degree in 11 subjects under the valuable guidance of 20 eminent supervisors, which is rarely observable at a college level because our college is situated in a rural and tribal area. So far, 32 students completed their PhD from our college and 20 students are registered for their PhD studies in our college, and they are pursuing their PhD under the different disciplines. The motivation from our academic coordinator, Honorable Sri M.N. Patil sir, have played a pivotal role in propagating quality initiatives in the college. Friends, as we know, microscopy is the technical field of using microscopes to view objects and areas of the objects that cannot be seen in the naked eyes, as said by Honorable Ramanujam. There are 3 well-known branches of microscopy, and I am also a student of physics, and I know little bit about the microscopy. So the 3 branches are optical, electron, and that of the scanning electron microscopy, along with the emerging field of X-ray microscopy. Optical microscopy and electron microscopy involve diffraction, reflection of electromagnetic radiations, electromagnetic waves, we can say, electron beams interacting with the specimen, and the collection of the scattered radiations or another signal in order to create the image of the sample. The most familiar type of microscope is optical, and we, the geologists, use in the beginning the optical or a light microscope, in which the glass lenses or a system of lenses are used to form the image, as we know. An electron microscope is that which uses a beam of accelerated electrons as a source of illumination. Electron microscopes are used to investigate the ultrastructure of wide range of biological and inorganic specimens, including microorganisms, cells, large molecules, samples, metals, and crystal, and much more, we can say. So today, renowned resource persons will speak on the microscopy in this workshop. Our team of Zoology Department, in collaboration with IQAC, under the DBT Star College scheme, have put lots of effort to organize this workshop, and proud to mention that more than 500 participants have been registered up to the last night, and the number might be increased now because on the Zoom we are having 100 participants because our link is for the 100 participants, and others teachers, they are enjoying, teachers and students, they are enjoying this lecture on the YouTube, and you can verify it on the YouTube. I am sure that this workshop will be helpful not only for the teachers of zoology, but also teachers for the science stream, and but also for the students in general. My best wishes for the success of this workshop. Thank you very much. Thank you.
Thank you so much, Professor Dr. R.S. Patil, sir. Thank you so much for your speech. Now, I would like to request our head of the Department of Zoology, Dr. R.M. Chaudhary sir, to please say a vote of thanks for the inaugural function. Dr. R.M. Chaudhary.
Good morning to members. It's my pleasure to thank all the dignitaries and stakeholders of this program. Firstly, I express my sincere thanks to our President of AGUP Mandal, Shada, Honorable Sri Bapu Sahib Deepak Bhai Patil for support and encouragement. I am also thankful to our coordinator, Honorable Makan Bhai Patil, for his constant motivation and inspiration to conduct programs. I would like to thank our principal, Honorable Professor Dr. R.S. Patil sir, for his motivation. I would like to thank our Vice Principal, Dr. M.K. Patel, who always support us to conduct such type of program. I am also thankful to our today's resource person, Dr. Ramanujan Srinivasan and Dr. Savanan Palani for accepting our invitation, and today they are with us to enrich the knowledge in my school. I am very much thankful to all the participants for their overwhelming response to this workshop. I must thank the organizing team for working hard to make this program successful. Thanks to everyone for taking the time to be here today and for listening to me speak. I am so grateful for this. Have a nice day and enjoy the workshop. Thank you all.
Thank you so much, Dr. R.M. Chaudhary. Now we are waiting for the knowledge to gain about microscopy. So we'll start with the technical sessions. So I would like to request Dr. Vasu to please take charge for the technical sessions. So Dr. Vasu, please.
Thank you very much, sir. I, Dr. Yogesh Vasu, Organizing Secretary, welcome you all for first technical session of this one-day national workshop on microscopy. I have given an opportunity to introduce our first speaker of technical session 1, Dr. Ramanujam Srinivasan, sir. He is from National Institute of Science Education and Research, Bhubaneswar. It is nice, sir. Dr. Ramanujam Srinivasan is currently working at SBS NICER, Bhubaneswar. He received his PhD degree from the Indian Institute of Science, Bangalore in 2006. He received his postdoctoral training at Temsek Life Sciences Laboratory and Mechanobiology Institute, Singapore. He joined IIT Indore in May 2014 and later moved to NICER in October 2014 and presently working there. His area of research is dynamics of DNA segregation and cell division. Welcome, sir. I request Professor Dr. P.S. Loar, sir, to chair this session. Professor Loar, sir.
Yes, thank you, sir. Okay.
Professor Loar, sir, is a chairman, Board of Studies in Zoology, and member of Management Council in KBCNMU Jalgaon. He is the person with outstanding research record, having experience of more than 25 years of teaching zoology at UG and PG level. Many students have completed their PhD under his able guidance. He is a man with a kind heart and continuously motivates students as well as teachers like us for research and academics. His area of interest is biotechnology and bioinformatics. Welcome, sir. With kind permission of session chairman, I request Dr. Ramanujam Srinivasan to present his topic, Microscopy, Reimaging Leeuwenhoek. Please, sir.
Yeah, thank you so much, Dr. Vasu and Professor Lohar for this great introduction. And so I'll just get started off with my talk. So let me just start presenting my screen here. I think you can see my screen.
Yes.
Yeah.
Yes.
Yes. Yes. So as you can see, since the National Microscopy workshop and a talk, and I have titled my talk in a very strange way, which is not usually the research titles that you will see. And since there are many of these college students, I thought what I will do is let us just talk about what microscopy is and how microscopy has changed our understanding of certain very fundamental things or things that we take for granted today. So that's why I titled my talk as reimagining or imaging Leeuwenhoek. With that, I thank all the organizers for giving me this opportunity and get started with this talk. So I think many of you know that the first microscope or the compound microscope was built around 1595 and early 1600. And it was Hans who built the microscope that you can see on the right hand side. I don't know if I could, I don't know how to show my cursor here. On the right hand side, you could see that. And then you see a famous picture of a person holding a spring in his hand. And that I think most of us know because that's Robert Hooke, and we know the Hooke's law on the spring's constants and everything. But we also know him for something else, which is on the side of his table, which is the famous microscope that is shown up blown up here. And he simply had a water flask functioning as something to concentrate the light to illuminate the specimen. And there is an objective here, and then there is an eyepiece on the top of it. I don't know how the cursor is actually, if I can. Yeah, okay, there it is. So here is the eyepiece, and then there's the objective lens here, and the specimen sits right down here. So this was one of the first early commercial microscopes built by Robert Hooke there. And I think from out of this, what came out is, I lost my cursor again. Oh, no idea where it keeps vanishing. I think there is some issue. Okay, so with this, what we know is he published this famous book called Micrographia. He just simply kept looking through these microscopes, and whatever he could see, he would make an hand drawing. And this is the first time that we even understood a concept called a cell was coined out of this entire microscope. So that kind of was a fundamental shift in understanding biology. And but what changed a little soon later is this man's letter to the Royal Society, Antony von Leeuwenhoek. What he did was he built an extraordinarily simple handheld microscope. And through this, he saw certain things in simple water, which he called as animal cules. And we know that we understand what these animal cules are as bacteria today. And these were extraordinary or extremely major shift in our understanding, because it completely changed our perspective of what we believed as life to be after we got these microscopes and after Leeuwenhoek's observations. And since then, the microscopy has undergone several changes that all of you might be seeing in several ages. So even in your college, you might have some of the simple microscopes here, which you may see here, which is just on any table, anybody's table would have this kind of microscopes. But a more complex microscope would look something like this, which only a departmental facility would have. And on the left-hand side, you can see here for the first time, they tried to combine microscope and photography, even when photography just had begun. So this kind of putting these things together, it took microscopy somewhere far beyond with what Leeuwenhoek and Robert Hooke had started off with. So with that, what we came to appreciate is that bacteria or microscopic organisms also come in variety of shapes and sizes, which we had earlier not appreciated. And in fact, here you can see this. It keeps disappearing. Yeah, you can see this E. coli, that is small dot there. And the eukaryotic organism that we all know as paramecium here, that eats up this E. coli and lives and thrives on E. coli here. And the large one that you see there is not some gigantic, it's a gigantic cell, and which is a bacteria. So bacteria size range from this tiny E. coli to this organisms called as Epulopiscium, which still is not the largest prokaryote. It's only the runner-up. So it's the second largest one. It's around 600 microns in size. So there is a bewildering range of sizes that you would see in bacteria. And what our lab is interested in studying some processes like this, which you would see in this time-lapse imaging. You just see that at some point an egg pops out, and then there is something out there and that keeps growing, elongating, and dividing. And pretty soon, the entire field is filled with this. So it's like explosion of the population growth. It just came out from one cell here. So it's one cell. So this is a spore of Clostridium that just burst open when nutrients are found, and they just born like as if they are born from an egg, and then they divide by binary fission. So these are the processes that we in our lab are interested in studying. So what we are interested in studying this process as cell division, and then also DNA segregation within these simple unicellular organisms, which are bacteria. So there's a small history to this cell division process. It all starts with Francis Jacob, with many of you in the college would have read about the famous Lacoperon. He is the Nobel Prize winner for discovering how genes and molecular networks work in cells. What he also did, his lab did, is isolated the first thermosensitive mutants of cell division mutants. And these were called as the filamenting temperature sensitive mutants, because on the top you can see a long filamentous E. coli cell. And then a plethora of papers later in 1992 or 1994 show that these are proteins. This mutant was in a protein or in a gene called as FTSZ, which encodes for this protein, which is a GTP hydrolysis protein that behaves very similar to the eukaryotic tubulin. I think most of us understand what eukaryotic tubulin is. And in fact, later crystal structures or X-ray diffraction studies showed that FTSZ, which this protein was in bacteria, shared very similar structure to that of the tubulin. I'm trying to get my cursor and it just... Okay, so this looks very similar to that of the tubulin. And then in fact, we have also actin-like proteins in bacteria now. All this is fine. So we get structures. We understand today that there are ancestral folds which evolved in bacteria, and today they are found in eukaryotes as well. And most bacteria utilize this FTSZ as a protein to divide. Not only bacteria, but also archaea do so. And then eukaryotes used actin homologs for cell division here. And there are other archaea which use completely different kind of proteins for cell division. But the most important question was, how do these proteins function? So as early as 1994, there was a proposition that bacteria utilize FTSZ, they form these ring-like structures. The cursor just comes and again vanishes somewhere. I just can't know where it is. Oops. Okay. Okay, yeah, let me just get to the talk then. So what was proposed in 1994, as you can see that there is a polymerization of FTSZ, which grows in length, and then that is what is guiding the septum synthesis, is assembled to a ring, functions as a guide. All this was seen, but what you can also see underlined in this statement or in this paper in 1994 is, however, none of these proposed structures has yet been visualized clearly in bacteria. And in absence of such evidence, a cytoskeletal role can only be inferred. So I think what you recognize here is we may have wonderful evidence from so many different kinds of studies and everything, but ultimately our desire to see something before we can change our concepts and our ideas as something that is inbuilt into the humans. And therefore microscopy becomes an extraordinarily important part of all these research and studies. So why visualize? Again, as I said, this has deep impact on how we think about things and how we frame ideas and philosophy. And given the example of current pandemic, which is the corona pandemic, no other virus has made such an impact into daily lives, not just because of the pandemic, but because in every newspaper or every way we can see this virus as soon as the pandemic started. In no other case of no other pandemic did we know how the epidemic cause looked like. So the image formation is something extraordinarily important for how much a general man or a layman understands things and how much science penetrates into our lifestyles. In fact, it was based on this simple visualization that when the concept of bacterium first evolved in the 1960s, Roger Strainier and von Neil, one of the famous microbiologists, they had defined two things, and they made an extraordinary statement in there. This one, that there are two kinds of organization that is found in life sciences. Just two kinds of organization. One that is depicted here, which is having these eukaryotic cells, and another one is this, essentially nothing. That was our concept of bacteria until very, very recent times. That bacteria are simply a bag of enzymes. They have no organization within them. There is nothing extraordinarily interesting about them. And in fact, their cell division was only as complicated as breaking a soap bubble, which any 2-year, 3-year-old kid will be playing. And they understood everything about bacterial cell division simply because if you pull this bubble, it will snap in the middle. And that is where the word binary fission comes from. And that was our extraordinary understanding of bacterial cell division until recently. Why was that concept? Again, it is simply because the size of the cell. It is very small. We could not visualize things very clearly because we needed extraordinary microscopes here to see them. And that is where microscopy again pitches in. So what you can see is one of the most famous model organisms, Drosophila here. The egg is depicted there, and inside which is a tiny human cell, which is this HeLa cell. Beside that, if you can, cursor has again vanished. Inside that, you can simply see this yeast cell, and above that, there's a small tiny line, which is the bacterial size. And if you zoom that out, you can see the bacterium above the yeast cell here on the leftmost corner on the top. And then, okay, for a comparison, here is a live image of a bacterial cell and a yeast cell for the size comparison. So it was really difficult to see things, and that is why this concept of bacteria had nothing and they should simply have no organization within them came from. But the entire thing changed with the discovery of fluorescence, and then with few scientists who won the Nobel Prize for creating an extraordinary palette of fluorescence that is available to us. So what is fluorescence? It is just that you excite something at some wavelength, and that molecule can then transmit light, which is at a higher wavelength that is visible to us. So using this technology, scientists have uncovered a lot of cell biology in these organisms. And it is this fluorescence that changed our view of what a bacterial cell is. And there comes a microscope that helps us to visualize this entire framework of what is happening within these tiny cells. And a fluorescence microscope, as depicted here, is simply consisting of a light source, which is back here, a mercury arc lamp shown here. It of course has the objective, which magnifies the objects for us to be able to see clearly. And then there are these filter cubes that are specific for certain kind of wavelengths of light. And there is a detector. Instead, we can look into the microscope, or if you want to capture, these are these cameras. So what are these light sources? So today there is a number of light sources that are so these are the simple components or the vital components of the microscope. I'm not getting into a lot more details about here, how they work and their light schemes and everything. So what we essentially need and consider about microscope is only these 4 vital things here. And light sources, depending upon requirement, you have a very simple and extremely somewhat cheaper, not very cheap, mercury arc lamps and metal halide lamps. And more famously now there are LED lamps that have the entire spectra that cover the entire visible spectra here. So these can be used as light sources for in your fluorescence microscopes. And this filter tubes, which forms the most essential part here, have 3 parts here. So I would really like to have a cursor here, but it keeps disappearing. Oops, yeah, it did come, but yeah. So here this is the filter cube from where the light enters of what you want to excite. But then there is this dark black line that you see is a dichroic mirror, which allows only one wavelength of light to be reflected into the sample that will be below here. So here is the sample. So the light comes in, it goes below here, but not all the wavelengths come. It's only one wavelength that comes. And then when the sample is excited, it emits fluorescence. And the fluorescent light that goes through is allowed to now pass through this filter that is called the dichroic mirror. So what it does is it blocks certain wavelengths, but allows some other wavelengths. And therefore it's called a dichroic mirror. And the emitted light passes through this, and there is an emission filter here, which again allows a particular wavelength to come out, which is where we can see the sample. And here will be your eyepiece, and you can see the sample. And these filter cubes come in variety of things for each different colors and excitation and everything. So one example is shown for GFP here, that you excite with this 450 base pair, and there is a dichromatic mirror of 495 which cuts off this wavelength. These are all the wavelength numbers, and then the emission of the GFP is what you see. So, and in the previous slide, you saw two things. One is LP and BP. What are these things? These are simply long pass and band pass. For what they are, oops, where is it going back? Is the long pass simply lets all the light that is beyond the wavelength to pass through. And band pass filters are much more specific. They allow only specific light to come through. So if you're doing multicolor imaging, you might want to look at the band pass filters here. So that is why we have different filters, which are, some are expensive, some are cheap, and depending on your requirement, you can always choose these filters and go and do what microscopy you would like to do. So the next piece comes the objective. So one of the most important things in the objective that many ignore or forget to think about is the thickness of the cover glass. You know, all of us use a cover glass when we prepare our samples and everything. So the cover glass comes with a certain thickness, which is 1.16 to point, or the objectives are tuned for a specific thickness. So in microscopy, most often we tend to use this number one cover slip, thinking that number one is the best one, but that is not the case. So 1.5 is the most optimal for most objectives that is built. And if you don't have the right objective, you might want to correct your correction collar here. Marked here, there is a ring in some of the objectives to turn around, which can suit your thing. And your objectives, some of the objectives are very simple. So different objectives are shown here. All of them are 10x here, but there are many glasses added into some objectives here. So what are those extra glasses? Because if you add extra glass, the light is going to be cut down. But these are important for correcting certain things when you want to see the image. So you can see on the right hand side image of a pigeon. Most of you doing photography would have known this. So when you image against the bright light, you would see this cyan colors and this red colors coming up. If you want to correct for them, your lenses have to be corrected for these extra colors that come in. These are the chromatic aberrations that usually come up in the light lenses. So these lenses are corrected for these aberrations, because in microscopy, you cannot afford to have these kind of aberrations. You would think your sample has those things, but your sample is not really having those things. So as you go on correcting for these things, the lenses become really expensive, and some of those lenses can cross nearly $10,000. But again, depending on your use, you can choose your objectives, and you might not always need the most expensive lenses. And one more thing to consider is the light. When you might want to see the biggest picture. You want to go higher and higher in magnification for everything. But you can see from the right hand side of this image that as you go higher and higher, what you would start seeing is losing light. So your image becomes really dimmer and dimmer and dimmer. So here are two examples shown here, the two images taken at the same setting, but with two different objectives which have a higher numerical aperture. So as the numerical apertures slightly increase, the brightness of the image can increase. And if you want to increase the numerical aperture, then the lenses again become more and more expensive. So the brightness is usually coming with the numerical aperture to the power of 4 divided by the magnification square. So that's the brightness of the image. So depending on what you are actually imaging and seeing, you can also decide what objective is best suited for you without losing your light. And the last thing in this light, because you want to capture the maximum light, are the detectors. And if you can see, the human vision is really low on that. So what you can see is really low. But today, the detectors or the microscope cameras have become extraordinarily sophisticated that they can almost detect 95% of the light that is coming there. So that's a quantum efficiency. That is the ability of the detectors to produce electronic charge from the percentage of the incident photons. So they may be receiving the photons, but if a detector cannot convert them into counts, you're not seeing them. So some of the best cameras today have really 95% efficiency, and we have almost reached the saturation there. You can't get better here. So we are at the limits of this detector sensing unless some technology really changes. So simply making it bigger and bigger, would it just simply help? And this should have solved all the imaging requirements, right? So, but that really not is the case, we know that. And that stems from one of the fundamental limitations of light or optics, which was given by Abe here, who told that there is a resolution limit. So we know this resolution limit for light if for green wavelengths around 500 nanometers here to be around 200 nanometers. So if you have this 200 nanometer, you cannot resolve two objects that are closer than 200 nanometers using light microscopy. So as it was pointed out in the beginning that there are different kinds of microscopy. So you can get to this with electron microscope to break down this light barrier. So what is this resolution? Resolution is the limit where you can distinguish two objects as separately. So if you can look at this line A, you can distinguish that there are two separate lines there, and you can see that the points can be distinguished. But even in B, the lines are so close together, but probably you cannot distinguish them because the light is overlapping there. And if you want to distinguish them, you have to probe them with something of a lower wavelength. And that is one principal problems that has been there with imaging bacteria. As they were so small, how do you resolve things within them? So if you want to study cell division in bacteria, or if you want to see things within them, you really need to get to resolving light or using light microscopy. You have to get beyond this resolution of light. So that has been one of the fundamental challenges in imaging and understanding molecular studies or molecular basis of these kind of localization patterns in bacteria. And that simply has to do with the biological scale, because as we get down and down in size from bacteria to organelles inside a cell and virus, we need much more higher resolution. But where is this problem of resolution coming from? Why is it, where is it coming from the light? So it's actually coming from something called as the point spread function of the microscope. Because although an object is extremely small and it is just a point, like shown here, a GFP molecule is just 1 nanometer. When you excite it and look at it in fluorescence, it shows up as nearly 100 nanometer size. So here is 2 nanometer molecule. It nearly shows up 200 times its size. So that is the spot that you would see in a microscope. And you really cannot get down to this 1 nanometer size here with the light limitation. So that limits our imaging to this 200 nanometers, and which comes from this function. So then are we stuck with this? Are we doing only this? So what? But with this kind of microscopy and limitations of the resolution and good microscopes and detectors, what we were able to do is to understand at least certain things in bacteria, like the actin homologs organizes into certain structures within the cells, which plays the cell wall, and that is what gives them shapes. And the cell division protein FTSG again forms helix-like structures within the cell, and that kind of compresses into a ring-like structure. And we understand a lot about how the ring compaction happens. So with light microscopy in place, we were actually able to get back to, in 1994, what was posed as a problem, that we have not seen cytoskeletal elements in bacteria. And we could also see cellular processes like DNA segregation here. So if you notice these red circles and just focus on them, you would see that there are 2 spots here that would start to move aside. So this is the origin of replication that is moving from one end to the other end within a small bacterial cell, and there are cytoskeletal proteins that are pulling them apart. So we were able to visualize not just static pictures, but also do time lapse with fluorescence microscopy and understand bacterial cell processes such as DNA segregation and cell division. And that changed again our perception of bacteria have cytoskeletal proteins, and the cytoskeletal proteins that eukaryotic cells that we know, actin, tubulin, and the cell shape that gives that is given by these 2 human cells are all originated in bacterial cells. So that changed the perception of how we thought about evolution of cytoskeletal proteins, where they came from. And today we understand that bacteria have cytoskeletal proteins that function in cell division, that maintain cell shape, that are function and polarity, that can do chromosome segregation and give shape in bacteria. And finally, the question that is raised initially that we did not visualize this, very recently in 2018, it was finally visualized, the cytoskeletal proteins doing this process of cell wall synthesis and how the cell constricts. Scientists were able to visualize these with some very high-end microscopy done here. So I think, and today we know bacterial cytoskeleton proteins are not limited to these three proteins. We know a lot more cytoskeletal proteins, and it's an expanding universe. We are discovering each year or each day a lot more family of cytoskeletal proteins in bacteria. And with that, we really need new approaches to study bacterial cells. So one of the things that is coming up is super resolution microscopy that breaks down this barrier of Abbe's resolution limit using light itself. And there are various ways to do this. So some of the techniques are called as structural illumination microscopy. Another is single molecule localization and stimulated emission depletion microscopy. And three of the scientists here, Moiner, Hell, and Bredzig, got Nobel Prize again for super resolution microscopy. So I think I will stop here with, in the interest of time, I guess, or if there is like even, am I good on time, or what is my, how many more minutes might I have? Can I?
You can continue, sir.
Okay, so in which case I will just go through quickly each of these, just three things, and give you one example of again how it is changing our understanding of bacterial cell processes here. So, yeah. So what is structured illumination microscopy? So this can get down to half of your light resolution microscopy, around from 200 to 100 nanometers here. And what is this and how do we imagine this? These are, if you have two patterns like this, we get more structural information. So you can see on the right hand side, if you had a meshwork that is crossing each other, and if you can retrieve back information from here, that gives you more information on more spatial information about what is there. So it's kind of a mathematical reconstruction after you have acquired images. So you acquired several images with kind of these patterns or line patterns overlaid on your image. And finally, you get one image which you can reconstruct mathematically. That is the structured illumination microscopy. And what scientists have used this is again to study bacterial cell division here. So in this movie, you can see several bacteria there are several bacteria in this field, and each of them, what you're seeing is a ring that is where the cell wall synthesis will be formed, or the cell wall synthesis will happen. And you can see how these rings are actually moving around, or they are becoming smaller and they are constricting. So this is something that has been enabled only by super resolution microscopy. You would not see such a clear picture of a ring with any other conventional microscopy. So you can again see some of these rings do become slightly smaller, and this is how bacterial cell eventually divides using the cytoskeletal proteins. And another example is to understand the chromosome itself. So here, if you can, again, on the left-hand side, you have wide field deconvolution, where you can visualize chromosomes in human cells. On the right-hand side, with super resolution microscopy, you can actually discern that there are two threads of these chromosomes, and these are the synaptonymal complexes when two chromosomes come together. And in below, we have another example of bacterial cell division protein FTSZ here, which forms spiral-like structures. Using conventional microscopy, you do not see much structure, but when you use super resolution microscopy, you can see them clearly as being helices. And STED can take down much further in your resolution. It can come down to 50 microns. And the simple principle here is that you image and then you immediately deplete the point spread function with some other laser, and you get to a point now. And you can get to the center of the point. And once you know the center, you can build an image. But this is a very iterative process of doing this repeatedly. All of these super resolution methods are a bit slow process. And using this, again, people have understood how bacterial cells assemble into ring-like structures. So you can see these small pieces of polymers that are coming together, and eventually it assembles into a ring-like structure. So they've used this STED microscopy or super resolution microscopy to get to understand how bacterial cell assembles the cytokinetic ring. So finally, there is the storm which can really take you down to levels of electron microscopy, like 30, 10 nano, 10, and that's in the range of nanometers. And this is another principle, like if you can imagine, there are threads like here, and I don't look at the thread at one time, but if I can imagine points on those threads, and if I acquire multiple points very rapidly, eventually I can reconstruct the same image. And this is extraordinarily depicted in this, I think, this movie. There's an Eiffel Tower that as an example of how STED works. So it's not working, the movie. Okay, fine. So here is an example. This is actually blinking. We are collecting single molecules here. And after collecting several frames of this single molecule blinking, finally we detect each of these particles, place them to the center, and this is computationally reconstructed that we can get imaging up to 5 nanometers of resolution or 10 nanometer resolution. So this is imaging a bacterial transcription factor. So with these kinds of microscope, we can really understand a lot of things, how cells function, how localization in cells happen, even within a simple tiny bacterial cell. And of course, one has to consider, if you're doing live cell microscopy, there are setups like to keep the temperature and keep the media flowing so that the cells are alive. But these are just things that you would know as you are doing microscopy. What are the things that is essential for your cell? It is not the microscope, but you should understand your biological question of what you actually want to answer it. So super resolution might not always be the best technique for you to use. It may look very good pictures, but all this depends on the biological question that you are asking. What is the question? And it is not dictated by what you want to see eventually. So it is the question that dictates what kind of microscopy that you would eventually like to choose. And finally, I'll just end with this, because electron microscopy is another method to see cells. And combining fluorescence microscope and electron microscopy is something that is catching up very rapidly. So at the bottom of here, you would see a virus structure that is inside a cell. And combining both fluorescence and electron microscopy, we can get extraordinary details about how things replicate within the cell. What electron microscopy cannot tell, fluorescence microscopy can tell you. And what fluorescence microscopy cannot tell, electron microscopy can tell you. And therefore, when you combine these two things, it forms an extraordinary powerful technique, which is called as the correlative light and electron microscopy. So we can use this technique to understand, again, cytoskeletal polymers, how they are moving around. So here is one of the fluorescent polymers inside a yeast cell, and how they look like an electron microscope. This single filament, it's not a single filament, they are composed of multiple filaments which bundle together. So with that, I would like to end my talk, and a real gratitude to Dr. Graham Wright, from whom I have taken a lot of slides and input on imaging. He's the director of A-Star Microscopy Imaging Facility, which has fantastic imaging facility right from the starting of some of the ancient microscope to the latest correlative light electron microscopy that they have. And the entire program is extraordinarily well coordinated there, and they can help you with a lot of things. And they have, but at cost, depending on the microscopy, there is a cost to it, understanding these things. And a lot of things are available in open source. Leica, Olympus, Nikon, Zeiss have on their websites a lot of things about microscopy that people can go and read about, knowing microscopy techniques and what. So I have taken a lot of this information from those and incorporated some of our own research into this talk that I have in how we understand bacterial cell cycle or cytoskeletal proteins. So with that, I would like to thank my lab members for all the support and financial support for DAE, NICER. DAE has been extraordinary in funding, and DBT and SERB for our funding support, and some of the past members and current members in our lab. And I would like, with that, I would like to end the talk and thank you all for listening. And I think what I could get across is, from Leeuwenhoek, with fluorescence, we painted bacterial cells that they have intracellular organization, and with super resolution microscopy, we are understanding more about this organization that is there in bacterial cells. So with that, I would like to leave and take any questions.
Yes, session is open for discussion and interactions. Is there any question from delegates or participants?
I request all the participants to ask queries, if any, to the speakers and interact with the panelists
May I speak something?
by raising their hands. They will be
Hello.
unmute.
There is one question in the chat box, Dr. Ramanujam sir.
Okay, let me.
What is the difference between band pass and long pass?
Yeah. So if I will just go back to that slide. Probably and explain. Okay. So what you can see here is a long pass filter, or one slide before. So this is the filter queue. I'm not able to get my cursor. That's a big issue here. I don't know. It's comes sometimes and vanishes sometimes. So the long pass is simply after particular wavelength of light, it would allow all the higher wavelengths. So if you're doing a single color imaging, say if I'm looking at only at GFP, I really don't need to worry, right? It is going to be emitting only in 455, it's its emission. And even if the other light is coming through, I can look at this green and I can just not worry about other things if I don't have any autofluorescence in my cell and everything. And if that is the only color that I'm going to get. But in case if I'm looking at samples that have autofluorescence, or if I am having samples which are having fluorescence dual color in the red channel as well, then that would not be helpful. So I'm going to see both the things here. Then I might want to image GFP. I might want to use the bandpass filter. It will just allow light only in the range of 500 nanometers to 560 nanometers to pass through that filter. It will not allow any other light. So that's the bandpass. The long pass would allow any wavelength beyond that.
Thank you, sir. Is there any questions from participants? Okay.
Okay, sir.
Dr. Basu, please proceed.
Now I request Dr. P.S. Loa, chairman of this session, for his concluding remark on the talk delivered by Dr. Ramanujam Srinivasan, sir. Please, sir.
Yes, thank you, Vasu sir. It's a nice and elaborated seminar delivered by Professor Ramanujan sir. He has, through his views on different aspects of microscopy. Since 1595, there is a progressive development of microscopy. He elaborated different aspects of technical details of microscopy, including numerical aperture, resolution, and use of microscopy in research, particularly with reference to the bacterial cytoskeleton. Being geologist, we use microscopy to observe protozoa, to observe histological details of tissues, to observe glucosazone crystals in biochemistry. Imaging technology has widened our knowledge in relation to the medical imaging as well as to the digital images provided by Hubble telescope and Perseverance rover on Mars. I remember when I was a student in 5th standard, for the first time I saw a microscope in a school brought to the laboratory of chemical department by S.R. Simpy sir. And this is the day of Guru Purnima. On the day of Guru Purnima, I must remember his dedication towards the teaching and learning. So it was a nice and precious moment for us as a student to access the microscope for the first time. I personally like the presentation of Professor Ramanujan sir related to the single molecule localization microscopy and corrective image and electron microscopy. Sir, I would like to tell you that for the first time in 1988, we have the access of electron microscope in Department of Zoology of Pune University. It was an excellent day for us. We saw first time how the image is magnified millions of times. Sir, I must congratulate you for your nice presentation. At the outset, I heartily congratulate the respected principal, vice principal, HOD of the zoology department, convener, organizing secretary, and organizing committee for providing us an intellectual feast through Professor Ramanujan. Thanks to everybody. Thank you very much.
Thank you. I just have one more thing to add, which I forgot at the end. I thought I should add at the end for the students' sake. So I'll just share my slide here once more for a moment and just tell this to a student. So if you're able to see my slide. So this is something like when you started building microscopes, you can see that everybody probably had an access to microscope at some point of time. The microscopes were cheap and the small microscope. Every college, every school had a microscope. But today with the advent of these extraordinarily expensive microscopes, it has gone beyond access to any students or any colleges. And some of the microscopes that I told you, I can tell you that only NICER has it. Not even any other institute in India does not have it. It's so expensive that even a university cannot afford in India these microscopes. But then students, so Dr. Manu Prakash here has built these paper microscopes,
Yes.
Foldscopes, which also have now incorporated fluorescence into them. And these are like available for 1,000, 3,000 rupees. And this is a microscope built. I just bought one of them. I had other things, but built one. And with the help of my son, we just took some pictures of fly here. You can see the trichome and the hairs there on the wings of the fly. And you can see microscopy just with this paper microscope. So I think making it accessible here and encourage students to see things around the world and see more of, there is a lot more biology to what the model organisms that we study in lab and research. I think the future belongs to those and not what we do in our labs. So we have studied what is to be studied and what is at the fag end, but really to explore life and biology, I think a great starting point for students is this. Just explore your microscopic world around you with these paper microscopes and you will find a lot more exciting things. And when you become a scientist or you take up research career, you will find a lot more exciting things than anybody else has in this field. Yeah, with that, this is something that I wanted to share at the end for the students. Thank you.
Yes, sir. It's a nice contribution towards the biological and life science society.
Thank you. Yes, this was from Dr. Manu Prakash Lab. He has really built wonderful things here.
Yes.
Okay, thank you, sir. Thank you, sir. I'm happy to present vote of thanks for the first speaker, Dr. Ramanujam Srinivasan, for his knowledgeable talk on microscopy. Thank you, sir. I'm also thankful to the session chairman for the healthy interaction and concluding remarks and participants. Interaction with the speaker and participant. Thank you, Professor Loar, sir. Thank you once again. Now it's time for the next session. It's my duty to introduce our second distinguished speaker, Dr. Sarvanand Palani from IISc Bangalore. Palani, sir. Dr. Sarvanand Palani completed his PhD in molecular cell biology from German Cancer Research Center, University of Heidelberg, Germany. After his PhD, he worked as a senior research fellow at Center for Mechanochemical Cell Biology, University of Warwick, UK. Dr. Palani received many grants from national and international bodies. Recently, in 2021, recent years, he received DBT Wellcome Trust India Alliance Intermediate Fellowship and presently working in Department of Biochemistry, Indian Institute of Science, Bangalore. Welcome, sir.
Hi.
Welcome, sir. For this second session, I request Professor Dr. A.T. Kalse, sir, to chair the session. Now, Kalse, sir.
Thank you very much, sir.
Now I introduce the session chairman, Professor Dr. A.T. Kalse, a member of Board of Studies in Zoology, Professor and Head Department of Zoology, NYNC College, Chalisgaon. He has more than 25 years of teaching and research experience. He published many research papers in national and international reputed journals. Many students completed their doctoral research under his guidance, and 5 to 6 are working nowadays. For his valuable guidance, he recently honored with national level best teacher award from the GESA. Welcome, sir.
Thank you, sir.
With kind permission of session chairman, uh, I request Dr. Sarvanand Palani to present his topic, Life Through Lens, Deciphering the Cellular Processes at Microscopic Level. Please, sir.
Hello, can you see my slides?
Yes.
Yeah, sir.
Okay.
Mm.
Is it still visible? The video is on?
Yes, sir.
Yeah, sure. Hello, everyone. Good morning, everyone, and thanks for the invitation. And most importantly, I would like to thank the principal, Dr. Patil sir, and Dr. Patel sir, and as well as Satish for the invitation. And it's a great honor to present today after Srini's talk. And I don't have to say much about the microscope history as well as the microscope different parts and how it can be used at different levels. And today's my topic is about the life is through lens. So all our life is through lens because we need a extra pair of eyes always in order to understand everyday processes. So in that case, when you think about cell, it's in a micron or nanoscale level that where we need a even a bigger and a smarter eyes in order to see. Eyes in the sense, I mean lenses. So my topic is about the deciphering the cellular process at a microscopic level. And who I am first, and I'm Sir Dr. Saravanan Pilani. I started my group in Indian Institute of Science at Department of Biochemistry last year, 2020. And it's been 1 year being back to India. And so you can see the slides are moving.
Yes.
Yes, sir.
So yeah, so who inspired me? So today's, as you guys all say, that's Guru Purnima. I should thank my gurus that who's my PhD mentors, Jocelyn Pereira, where I got my PhD from German Cancer Research Center, and followed by moved to Professor Mohan Balasubramaniam's lab at University of Warwick, who's my postdoc mentor. Who, whatever I know today, it's all because of them, and most importantly, microscope. And I was trained as a biochemist during my PhD time, little bit of microscope, and I moved to Mohan's lab where I learned the whatever I know today about microscope. And with that, what my group is actually doing and what I know about the science from my side. So basically, I've learned yeast as a model system to study how cells divide. So if the cells doesn't divide and we all end up in aneuploidy, and that leads to cancer. So the most fundamental process of a cell to divide and give a healthy daughter cell. Then only we all propagate, and then we divide, and then we lead a healthy life. So the final cut, I'm interested in the most important process of a cell cycle, which is mitosis to cytokinesis, where the mother cell decides to divide. And what is the principle behind the division, and what makes them divide and what makes them not to divide. And that's the most important aspect of it. And here I'm most interestingly, I'm looking at the aspect of the cell division is that the kind of a ring formation happens between the mother and the daughter cell, and that determines when and where the cell to divide. If that is not positioned and that is not properly guided during the cell division cycle, and then we will ended up having a multiple abnormalities such as like chromosomes and then nucleus, and that leads to aneuploidy. And this is the process where I am interested in. And I'm sure Srini also knows about, and he's also one part of this particular research was happened in Singapore when he was a postdoc, where they isolated successfully the ring structure from dividing yeast cells, and then they contributed one of the state-of-the-art technique that where you can artificially make them constrict in the presence of ATP, because this is a motor-driven process. And I've used two important model system. One is budding yeast, it's a Saccharomyces cerevisiae. Another one is fission yeast, Caesarosaccharomyces pombe. And this is the two model organism I use in my lab to understand how cell divides. And as you can see, all this is possible using a advanced microscope as well as the recent imaging techniques. If you're not able to use any one of this, and we are not able to see such a beautiful process, what's happening, a cell which divides in within 90 minutes. So as you can see that every time they want to divide, they have to assemble and then disassemble. We call it a divisional apparatus in every 90 minutes. And then they have to continuously do this process. And it's one of the fastest process when you can imagine compared to human cells and then the yeast and the other lower eukaryotes. And in this case, we have to capture not only the division and also that every single part of it, like how this assembly of this ring happens and how they are pinching from the daughter, from the mother cell, and how the daughter become a mother again, right? So it is a kind of a continuous process, and we need to have a fluorophore that I'm going to talk about very soon, and how we are going to capture such an event which is very rapid. And in order to capture such a rapid event, we need an advanced microscope as well as the fluorescence, which can enable us to capture this most fastest process. And as you can see that where we started, like for example, as I said, we all have powerful eyes when you are a child, and then slowly we lose that power due to aging. And also that we can, certain things we can see by human eyes. As you can see your fellow person, you can see liver, brain, heart, chicken egg, donkey, dog, everything by your eyes. And we need a magnifier when you want to see your own palm, like for example, tiny details in your palm. Then you need a magnifier, such as if you want to see a frog egg or a human egg and all that. And later we need a conventional light microscope, and that's where we are all fascinated when we are at school, that the moment we see a microscope, whoever it is and whatever, they don't have necessary to do science. Even as Srini mentioned the last of his slide about foldscope, the moment the foldscope arrived, I'm sure that many people bought immediately, because even my granny was using a foldscope to see a beetle leaves, what is there. So that much of a curiosity comes only with microscope. I'm not saying that all other science techniques are not important, but I'm saying that the curiosity driven process always comes with microscope. And later then you can see a conventional light microscope where we're able to see a plant cell, dissection of leaves, as well as human blood cells, bacteria, yeast, and several organisms like tiny organisms. And later we move on to electron microscope in the middle between conventional light microscope and electron microscope, and then we got now an optical based microscopes where you have a storm, stem, and spinning disk microscope, confocal microscope, and so on and so forth. And if you wanted to go much more in detail, that's where it comes to X-ray crystallography, where we can see DNA, protein, and so on. So the way we look at microscope, that's where we see ourselves that, wow, I didn't know that, these guys move. Like, for example, some organism moves and some organism doesn't. Like, for example, I'm sure being in a zoology institute that you guys would have collected a sample from a pond and then looked at the diatoms, tardigrades. There are so many things available, and then everything is fascinating, the way we look at things and the way we want, what kind of microscope we use it. And the moment we add something to it, such as like a dyes or something which go and stain, like for example, the membrane of the cell, or it penetrates into the membrane, and then when you see the nucleus, or some other structures inside the cell, that also makes us fascinated. So the microscope is nothing but as a fascinating tool. It's not only for us, it's for kids to the old age people. So why we need advanced microscope? So why we are not satisfied with the light microscope? Of course, that for example, if you compare the old Nokia phone, that solves all our problem, right? So we can communicate with anybody, we can message them, we can do anything. But why do we need a smartphone now, right? That's the difference. So we, like all our great scientists, we used the light microscopes, like in the old days, all the basic discoveries, how cell divides. everything was seen only in the light microscope. And now the advancement is moved, and we want to do everything faster and more unique and more fascinating way. And that's why we need a smartphone in a hand. The same thing that if you think about it, this is the old microscope, hook microscope. That is our Nokia phone, right? So that's where we were using almost like I don't know, like 15 years or 20 years since the microscope arrived, so since the phone arrived, cell phone arrived. And later we moved on to optical microscope, where we have a lot of light sources. Like for example, we had it started with halogen lamp, and then moved on to a mercury lamp, and then we went on to a laser power, and now we have a super power LED sources, and more and more, and even high power laser source. And those things are changing. And also cameras. So the camera, before only our eyes are cameras. And I still remember when I was in my bachelor's and VIT, we had a small light microscope. We were using a kind of some kind of that time the mobile phones come with a camera. So we put the camera, the mobile phone camera, onto that eyepiece and taking a picture, and we are so excited, and we are taking videos and all that. And now we have a CMOS camera, is a EMCCD camera, and so on. And those cameras are capturing as 95% of the quantum efficiency, and you can see every single detail. So for example, that with this old phone, we can see only messages, we can call. But with the smartphones, we can see WhatsApp, we can see Facebook, we can see our emails, and everything, whatever we can do. The only thing was that as it comes more smarter and smarter, it's also more expensive. As nicely applies this also with the old microscope, it's cheaper and it's more reliable, but smart microscope also that it's more expensive. And as you see, the basic microscope, it's very simple. And like, for example, even we can buy through Amazon and Flipkart. Before, we have to go to a scientific instrument shop to buy it. Like, for example, I have my own microscope at home. During the lockdown, to entertain my son, so that I can immediately buy one microscope and keep it, take anything, whatever he grabs, and put it in even a breadcrumbs or a fungal contaminated breads, all this we can put it in that, and then we can see and make people happy. So as you can see, the microscope, basically it's a very simple, like you need an eyepiece, objective lens, and the focus knob, ups and down course, and fines adjustment, and light source, a simple light source. Nowadays everything comes with the LED light source, even a white light, and then the condenser lens and the mechanical stage where we can put things on. And now, what is the current microscope? So there are leading companies. It's not only one or two. There are many companies, and the most prominent companies, what the advanced microscopes, or the upright or the inverted microscopes, are made by Nikon, Olympus, Leica, as well as Zeiss. And there are also many other companies. And also that all these companies are making the body of the microscope. And there are different parts of microscope, such as camera. So the camera comes from a different company called Photometrics, and they make always advancement. As we think that microscopes are developed over the years, no, it's kind of developing every month, I would say, because not just one part is developing, or also other part is there are new filters, there are new fluorophores, there are new camera, new LED source, or the light source. There are so many things happening. All this come together, and we have one smart unit, which is called a current optical microscope, which can be used for many aspects of it, such as you can take a simple stained cells, or you can go for a fixed cells, or you can go for a live cell microscopy, or you can go for an advanced SIM or STORM or PALM and structurally illuminated microscope. So so this is a principle. I don't have to talk much about this. What are the advanced microscopes? Srini went in depth of it. So you can see a different optical microscopes, what we mostly use, and TIM and SEM, or the electron microscope, transmission scanning electron microscope, and then we also have a lot of atomic force microscopes, and then and so forth. And most of the things that what we use in a regular way, that we use wide field microscope, and whether you can use a LED as a light source, and a simple camera, EMCCD camera, will help with it. And then if you go one step higher, it's a confocal microscope. I'm sure that many universities at the minute are buying wide field microscope or a confocal microscope using a laser as a light source, or a LED as a light source where we can immediately see things, and which kind of a detailed understanding of what we are looking at the samples in the case of cells and so on. And then we also have a near field microscope, such as super resolution turf based microscope. Mostly turf based microscopes are used for a single molecule imaging. And so we started with a simple light microscope, and at the moment we moved to a super resolution microscope. In between, there are so many variants happened all in the last 2 decades. It didn't take so much time for a physicist. We all, as a biologist, thank to the physicist and chemist who all come together. A microscope, it's a kind of an amalgam. It's not the biologist can't claim one side because it's a kind of a physicist, chemist, as well as biologist. Altogether, it's a kind of an amalgam where we call it a microscope. So the reason Nobel Prize was given in chemistry in 2014, where Stefan Hell was very close to my lab where I did my PhD, and then Eric Betzek as well as William Morner, all together they got for the super resolution microscope Nobel Prize in 2014, and that kind of changed the way how we look at things. Before we were so microscope is one thing that we never get satisfied. It's a, like, for example, that if you get a iPhone 10, we are not get satisfied with iPhone 10. No, they are keep on updating, we are keep on buying the same thing. So it's a kind of a fascinating thing, so that we'll try with this and we'll see what we didn't see. For example, something what people didn't see 10 years ago, now people are seeing very clear. And maybe what we are seeing now within the cell, maybe we are not, some people are going to see much more in depth after 10 years. So this is our microscope. It's constantly evolving process. And most importantly, that, okay, you have a microscope and you have one of the best microscope, and you put the specimen, how are you going to look at the specimen without, if it is not fluorescent? Right? So we are not going to use a light microscope, we are using an optical microscope. We want to illuminate something, and that has to have a fluorescence in order to excite and get the emission and so on. So here I just put a cartoon saying that if you take a cell and the moment you throw, one of the common stain what all of us use is the DAPI staining, which stains the DNA. And then the moment you add the DAPI to the cell, it's a kind of highly cell permeable. It goes to the cell, and then you can see our DNA is in blue color. And this is one of the common stain which many people have used, and that's how the cell makes the first thing what people do. Oh, I want to see the DNA. Okay, the moment you take the DAPI and add it to the cell, and it's nicely permeable, and you can immediately see them inside. So the fluorescence, the word starts with F and followed by so many methods and so many techniques have been used, like, for example, FRET, FRAP, FAX, FCCS. These are all the different methods for different purposes. If you go and type fluorescence in PubMed today, it started using the fluorescence, the word started using since 1898 until 2021, that almost like 7,31,091 results hits you get. That many papers, abstracts using the word fluorescence. Without fluorescence, there is no use of microscope. Yeah. So the fluorescence is a new era of imaging. So the fluorescence, the first fluorescence, I'm sure that all of you are aware, is a GFP, a green fluorescent protein, which comes from the Aquaria victoria, and which is identified or completely kind of, when you look at the history of Osamu Chimura, how he identified and how he characterized that, it's kind of mesmerizing thing. So where he identified this Aquaria as is found a green fluorescent protein, we normally always call GFP, and it has got 11 beta sheets, and then which is kind of emits at 488. And followed by modifying this particular green fluorescent protein GFP with several mutations or several additions and deletions of this particular protein, and give us different colors. For example, this EGFP, with, and then you have a M banana, M orange, TD tomato. TD stands for tandem repeats of the tomato dye, and then tangerine, strawberry, M cherry, M grape, raspberry, grape 2, plum, and even we have new dyes such as Kate 2.0, and so on and so forth. So this fluorescence changed the way we look at cells. It's not only the microscope, the camera, or the lens we use, or the objectives and things like that. It's most important. It's a fluorescence. how we make the cell fluorescence. That is very important. So the fluorescence, it's one of the most important criteria in order you have to visualize things in live. Like for example, we most of the time, like for example, until 1990s, that people have used always to fix the cells. You fix and then we make an antibody and then we image using the antibody, and that is conjugated with some dye. And that era is over now. And still, in some cases, we are still using immunofluorescence, which is using the fixed cells. And now we wanted to see what is happening in live. That is the kind of an excitement what we want to see. So this protein is there in nucleus, and people have seen in 1980s and 1990s. But we don't know whether the protein is always in the nucleus or the protein also comes out of the nucleus for 10 minutes and going back to the nucleus. And that is the fantasy what we wanted to see. So if you think about the fluorescence, and we, as I said, that you have the excitation, and then you have a lower energy and the longer wavelength with an emission where you can capture different fluorescence. For example, green you can excite with 488. If it is red, M cherry, we can go with the 555, and you have a far red which you can excite with 647. That's excitation wavelength what we use. And we have a primary fluorescence, and also that we can also use an indirect fluorescence by using primary and secondary antibody. The secondary antibody carries the dye. And we have fluorochromes, which has dyes, such as the DAPI is also one of the dye, and so on. And what is the advantage of the fluorescence? Why fluorescence is important when you talk about microscope? Because we wanted to see things. We don't want to see the outer layer. We want to see how that particular organelle or particular protein and where it localizes within the cell. And that is the most important key thing for any research. I mean, in biology. So in the case of the advantage of fluorescence is that it's easy. Like for example, you can tag them, or you can buy a dye and then you can add it to the cell, and then it directly goes. And if you take it to the fluorescent microscope, and you can see, for example, DAPI and so on. And also that you can also fuse GFP along with your protein of interest. Then you can see where that protein is localized, whether it is in the endoplasmic reticulum, or it's in the nucleus, or in the mitochondria, and so on. And you can also see that, oh, you are interested in 2 proteins. I want to see these 2 proteins, are they co-localizing, right? So that, like for example, you have a protein A and protein B. So and people have shown, one paper has suggested this protein A is localized in the nucleus and protein B is localized in the ER. But are they co-localizing at some point? Either A goes to B or B goes to A at that kind of that particular localization. That you can see with the co-localization studies. And also that we have a dynamic range. That's what I'm saying, the most important, how in the live cell dynamics each proteins looks like. So as I said, you have a total like almost like, I don't know, 40 plus fluorescent proteins at the minute in the market. We can get it from our gene, or we can synthesize this particular gene. All these are open sources. We can have there. For example, there is a new green for most of the people who are using like a green fluorescent protein, we call it GFP, and then people made a superfold GFP, and now the recent green dye is fluorescence protein called M neon green. This is like a 2 times more brighter green color than the existing GFP, and so on. And these are all the different excitation and then emission and how it works in live cells. And what is the advanced in fluorescence? That is also important. Okay, this technique, all this GFP based tagging or all the fluorescent protein based tagging are there almost for the last 15 years. And now we have moved on. That's why I'm saying that microscope and microscope related things are constantly evolving. Every month there is a new paper coming in and saying that they've identified a new technique or a new tool in order to visualize what was complex earlier, like 10 years ago or 5 years ago, even a year ago. And now we can able to solve the problem. So there are, based on, like as I said, you can use antibody, which is for a fixed sample, use immunofluorescence. And recently there is something called nanobody, which is the FCFH fragment of FAB fragment, and which is only like 12 to 15 kilodalton that can be used both for live cell as well as fixed samples. And also that nowadays we have something called aptamer based imaging, which we can also use for a live cell imaging and so on. And also there are certain things, for example, that if you wanted to tag your protein of interest with the GFP, and suddenly you realize that, oh, I don't want in GFP, I want it in M cherry. And suddenly you decide, no, I don't want M cherry, I wanted to have in far red color. So you cannot keep on doing, like, for example, you cannot keep on making your cells with the GFP separately, RFP separately. Of course, that is what people were doing. But what is the advanced thing happened? There are two companies. One is a Promega, another one is a New England Biolabs. They come up with the two important tags. One is called halo tag, another one is a snap tag. Basically, this tag doesn't have any fluorescence. Okay, so you tag this particular protein. There's a halo tag which is like 20 kilodalton, and snap tag is also roughly 20 kilodalton. You fuse this particular thing along with your protein, and you want to image today with the green color, and then you add the dye which go and then conjugate with the tag, either it halo or snap tag. The dye is 488, Alexa Flow 488. We call it snap tag dye 488. And the same cell you can image tomorrow with a red color, and this tomorrow day after you can detect with a far red color. So this gives a huge flexibility. So you don't have to make multiple strains or multiple cell lines in order to image. So you can make one strain either with the halo tag, and then today you image with 488, and tomorrow that you want to image other protein with the GFP, and then you can change this by just adding the dye, so that you can decide and change. And that gives a lot of flexibility. Not only it also saves a lot of time as well, because in order to make each strain will take at least 3 weeks. Now you make one strain, and then you can image whatever you want whenever you want, and you change the color. And this is the advantage of both halo and snap tag, and this is the advanced probe at the minute available in the market, and this has been widely used, and I've also used for my research during my postdoctoral time. And another important thing, okay, now we come to the topic, which is cytoskeleton. So that's what Srini was talking about, bacterial cytoskeleton as well as the eukaryotic cytoskeleton. Cytoskeletal proteins are kind of, you cannot touch them because they always form dimers, head to tail dimers, and you cannot tag them either at the N terminus or the C terminus. You cannot fuse anything, either GFP or MC, anything, because then they will not function. The protein is not functional, then the cells will die. So there is no point, like make them die, because those proteins are very essential for the normal function. So then people have come up with some dyes which can directly, if you can add it and directly go and bind. For example, as I said, DAPI. So you can add DAPI, it can go and bind, and then which can make the, like what you see here, the blue color, it's a DAPI dye, and then the red color is microtubule. And there are recent dyes are coming where you don't touch the protein, you just add the dye, and the dye directly goes and binds to it. And also that if you wanted to sense that calcium, or for example, most of the people check the calcium, the level of calcium in particular. For example, when you are having the wound and the calcium level goes, and people want to sense that what is the calcium level, and then people now come up with the calcium sensors, which is also small fluorescent dyes. And also, not only for calcium, there are many metal ions can be detected using these sensors. And also that is there a pH change that can also be sensed using this kind of particular fluorescent sensors. And for example, now we talked about fluorescence, right? So now we can move into, you wanted to see one particular organelle or a compartment within a cellular, and how you are going to stain, because you don't want to tag a particular protein. I wanted to see an organelle such as nucleus. As I said, very simple, that you can add a DAPI and it goes and stains the nucleus. Or you wanted to see them with the GFP, then you can tag some of the, you choose one of the nuclear protein. For example, here I gave an example of histone H2B with the GFP. There you can see a very nice nuclear signal. And now you decided you want to see endoplasmic reticulum, and there are dyes are available where you can buy. It's called berpheldin A, and you can that also. So that now the advanced is that it's not that anymore that 10 years before that we stuck with only one dye with one color. So there are so many companies are coming up with a lot of dyes and with the different colors. Like for example, you can see mitochondria with green, and then ER with red. So before it was there was no such flexibility, and now we have a lot of dyes are available where you can check at the same time multiple compartment on the same time. And for example, here is one of the example of mitochondria where you have a mito tracker, which is available. As I said, mito tracker 10 years before are available only in GFP. Now you have a mito tracker available in red, green, and orange colors. So then we can see a nucleus Along with DAPI, you can stain nucleus, and then you can stain mitotracker, and you can see mitochondria, and also lysozymes. There are quite a lot of new things are coming up. You can stain at the same. You can see the entire cell. You don't have to color like as we do in school as well as in colleges. We draw a cell and then we color this color, this color. Now we can do it in live using this particular fluorescent dyes and using advanced optical microscopes. And most importantly, it's not only the compartment, some of the filaments, and we have filaments, or we call it cytoskeletal elements such as microtubules and actin and myosin, intermediate filaments and septin. On all these proteins, you cannot touch them. I mean that you cannot tag them or fuse them with GFP, because then they will become not functional. So in that case, a dye or a surrogate marker becomes very useful. For example, lipid, if you wanted to see a lipid around it, and then you can use some kind of a fluorescent cholera toxin. That's a new research came up, and you can put them, and then it goes nicely mark all the lipid raft. And the case of actin, if you want to see this, I've used for myself for the last 8 years. There you can have a 17 amino acid peptide which fused with the GFP. And this peptide recognizes all different kinds of actin filaments, actin patches, all different actin structures, so that you don't have to use. So this is the one of the most important thing happened almost like 12 years ago. This kind of revolutionized the field, finding this life fact 17 amino acid peptide fused with GFP. Then people have started looking at actin live, how actin like suddenly it forms a filament and suddenly it becomes a patches, and then how this turnover is happening. Until then, 12 years before, what people are using is always the fixed cells. So you fix the cell and then you go for a dye. In fixed cells, you can see a snapshot. It's like an X-ray crystallography, because it's not a protein is always in one state. Protein is constantly changing. X-ray crystallography is a good example for a fixed cell. It's kind of one snapshot. Like for example, taking a photo and taking a video, that's the difference what you are seeing. So what people are doing last 20 years before, everything was a snapshot. You don't know what happened 1 minute before and 1 minute after. And we think that that person was alive at that time, but maybe the person was not alive 1 minute later, right? So that is the thing what we didn't know 20 years ago, but now we know everything in depth at a nanometer level scale, where we can look at all this filaments, movements, and as well as the turnover. So now I'm going to talk about that what I've been doing using this microscope. So for example, as I said that I'm using most of my time the spinning disk microscope and using all the fluorescent dyes, all the fluorescent tags I've used, using budding yeast as one of the model system. As you can see here, I tagged two important proteins. One is the septin in blue color, and the magenta, it is a myosin, is a motor protein. As you can see, I can lively see that when you can see the blue color, that it's kind of a collar, and then it's split into two, and then the pink, the magenta color disappears. And this is not possible 25 years before, or even 20 years before. And now we can nicely capture. This is a single cell. You can see a daughter goes out of mother, and then the new daughter comes. That this kind of resolution what I'm talking about. Not only advanced microscope, it's also a new fluorescent tags and the way we capture the image using advanced cameras. And the other thing is a Pombe, is a fissioning cell. It divides, it's a kind of a spherical cell. As you can see, the actomyosin ring, that's a divisional apparatus which is made, and then the ring constricts, and that gives the license for the cells to detach from the mother cell. And also that, as you can see, this is a mammalian cell. As you can see, you can capture every single detail of it. This is the cortex, and we are looking at some kind of a filament forms, and the filament is kind of endocytes into the, as you can see that the aromates pass, and then it forms kind of a spiral kind of a ring. And one important thing is that nowadays that we are talking about imaging as well as fluorescent tags, and there are also drugs. So the inhibitors, where you can perturb a cell, what kind of structures the cell can form. For example, what you are looking here is that LifeAct GFP, what I was saying, is a small peptide fused with fluorescence. Before, people were seeing actin structures only by fixed cells and using immunofluorescence. And now we have this LifeAct GFP, where we can see the dynamics, how the small dots become a cable, like a kind of a thread, like a track, and how it's going back. And there are some inhibitors where they can particularly kill the patches, because the patches are made by a complex called R23 complex, and this particular inhibitor called CK666. So now what you can see, I'm going to play the movie. If you can see, all the patches are becoming cables, and then I wash off the drug, again they come back to normal. So this kind of thing was not possible 5 or 10 years ago, and now everything is possible. So it's not only you can image the protein, what was not possible, it's also you can add the drug, you can perturb the function of the protein, and you can wash off the drug, and then you can see what happens in the absence of a drug. In the presence of a drug, you don't see any more dots. After I wash off the drug, again the dots are coming back. That means the drug was inhibiting a complex which was important to make those dots. We call it patches. And after you wash off, and then you can see the cables are coming back again. So, and the other important thing is also a single molecule imaging, right? So now we talked about only the cellular compartments, how the cells are doing it. So now you purify the proteins, and that is the advanced thing is happening. And this is one of my paper where we did this, purified the motor protein. And the motor protein is nothing but, if you can imagine, actin is it's a filament, it's a kind of a train track, and the motor is like a train. Okay, so we fix the motor on the surface of the cover slip, and then we purified the myosin, the motor, and then we put it so that the motor is constantly moving. And this is a turf based microscope where we can see image only to certain surface level. It cannot penetrate into deep, and where we can do all the single molecule tracking. And also that, as I said, it's not only the drugs or the inhibitors can be used only in cells. We can also purify proteins, and also you can use a turf microscope and add the drugs and see it. And what you can see here at the bottom, actin, it's an actin, and actin coated with the tropomyosin is another actin binding protein. And the drug here, sphingolide. Sphingolide is a drug which is known to chop the actin filaments. The moment I add the sphingolide drug, as you can see, the actin filaments are completely chopped. But the same thing is not happening when I protect the actin filaments with a protein called tropomyosin, because it's nicely protect. It will not allow the drug to act on the protein. So these kind of things we can use a turf-based microscope, and where you can image a single molecule. For example, I always use the purified proteins, and then you can label them, and then you can use it, understand the stoichiometry of it. And as Srini also touched at the end of his presentation about the advanced reason, because you can put the advanced always with microscope, because it's constantly evolving, it is always advancing. So we have a lot of new things that are coming up, such as the storm palm and the structural illumination microscope. So you can see the left and the wide field microscope image, the same thing was captured with the same, how much detail you can get to know about it, right? So it's completely blurred. It's like taking a picture with using a Kodak camera and then taking a picture with a DSLR camera. That's the difference you can compare here with the wide field microscope as well as the structural illuminated microscope. And also that here we cannot at the minute, it has got certain limitations. We cannot go for live, because if you go for a live, and it has to put a lot of laser power to capture such a minute detail, and that will kill the cell. So the people are coming up and advancing the methods without killing the cells, and they are increasing the amount of the fluorescence. That means developing the fluorescent probes, so that require very less energy. That means a less laser power without killing the cells, so that we can see such a detailed thing using a live cell. And also you can see a recent methods are coming up where you can look at the centrioles, as you can see in the conventional microscope, where you can see it's like a dot, a green dot around red. But the same thing you can do with the 3D structural illumination microscope. You can see in-depth detail. And more recently, that I'm sure next time if I get an opportunity, I'll definitely talk about this. It's called a DNA paint. It's kind of oligonucleotide based painting, and also a peptide based painting, where people can see even more, like kind of a 10 to 20 nanometer resolution. And that's what people are imagining for the last, I don't know, 50 years, that how to go and then see in that such depth. And this is possible. And there are a lot of papers coming up with this DNA and the peptide based painting thing. So, and this would be my last thing. So as I talked about, you have a fluorescent protein, which you can tag with your proteins, and then you can image. There is a limitation comes in, and what will you do? So this is one of the things which I kind of developed during my postdoctoral time using synthetic biology. tools in order to label the proteins. So where you can introduce, well, as we all know that we have a 20 natural amino acids. So that's what all our proteins are made up with. And we can introduce an unnatural amino acid on a protein where it was difficult to tag. For example, you cannot fuse a protein with the GFP or something, where you can put a fluorescent unnatural amino acid into a protein of interest. There we can directly look where the protein is localized. Because then in that case, you have a flexible, you can put the unnatural amino acid wherever you want on the surface of a protein. And this gives a lot of other advantages as well. It's not only for fluorescence, because fluorescence is one of the usage of using this unnatural amino acid technology or synthetic biology methods. It's also used for photo cross-linking and photo cage and so on. And this particular method works from bacteria to zebrafish, like you have a multiple, across scales. And one of the example which I've done using this method, where you can put unnatural amino acid for biorthogonal labeling, where you can mark. So far, no one has marked the tropomyosin. No one knows how a tropomyosin localizes into cells, and where we can now use the unnatural amino acid based technique, where you can localize a protein and see that where it is particularly localizing within the ring-like structure. And in summary, that the fluorescent microscope, as I said, it's a rapidly evolving or advancing the way we look at things. And also, it's not only the microscope, the body of the microscope remains the same, except few knobs are coming or switches are coming. But in outer the microscope, such as the camera and the filters and the light source are changing eventually, and also the software. There are a lot of softwares where you can analyze it. That is a completely different setup. That it's microscope is one part, and how you image it's one part, and how you are going to process them. Processing is the most important. You can have a beautiful cells, but if you are not able to process it properly, then we cannot able to sell the story, or we cannot able to present it in a good way. So that is a different thing. And also that a lot of probes, what I mean is tags and fluorescent proteins are all available. And also that what many of the technical advancement of related to microscope and microscope related stuff are happened in the last 30 years. And as I said, it's a constantly evolving process, right? It's like, like Windows 9, Windows 10, Windows 11, it's constantly coming, and we don't have to wait for 2 years. Within 2 months, we have a new thing. And we have to choose a right protein, the fluorescent protein or a fluorescent dye for your protein of interest, and then you use the right microscope to image to achieve it. So as I said, so in 1981, we got the first 1G, and now we are talking about 5G, because the advancement is totally happening. And that is what exactly with the microscope as well. So we started with Hooke's microscope, and then now currently we are in the middle where we see the spinning disk microscope, and we already moved to a fold microscope, fold scope, which was made by Manu Prakash. And now every kid, I'm sure, having this at home. And I'm sure that I would encourage also the colleges to have this full microscope kind of exhibition, or some kind of talk, and people that kind of encourage the kids like to get into this job. And most importantly, I would like to thank all of you for your time, as well as for your invitation. And at the minute, I just started my group. I will be hiring people. If someone is interested for a JRF or a project associate or a post PhD research associate, my welcome grant will be starting soon. So I would like to get some applications as well, if someone is interested to do this process, what I am doing at the minute. And I thank DBT, ISC partnership and ISC startup grant, and thank you all.
So thank you very much, sir. Now the session is open for discussion and interaction.
Thank you very much, Dr. Saravanan.
Please,
Is there any question from students? Just I'll check in the chat box. Just wait, sir. Participants, you can share your question in chat box if anyone have a question. Dr. Kalse sir,
Yes, sir.
I would like to add something here, if you permit me.
Yeah, yeah.
I would like to share one of my paper which was on which we have used fluorescent microscopy. So
Right,
Dr. Saravanan, can I share my paper which will show you image of sperm fluorescence?
Yeah, sure. Yeah.
Just a minute, sir. So that it will be useful to the participants also. I did my postdoctoral fellowship in Morgantown, USA, after my PhD in 2005 and 6. And then I was a postdoctoral fellow in CCMB, Hyderabad. So there, at both the places, I worked on spermatozoa. And in USA, Morgantown, I worked on the immunocontraception. And 2D, I used the technique 2D electrophoresis to separate the sperm proteins. And here in CCMB, I worked on the maturation of spermatozoa, the transit of spermatozoa from caput to quad epididymis. What are the changes which are taking place in the sperm proteome? The sperm may be upregulated or downregulated or may get phosphorylated. That was my work, and we got some proteins which were upregulated. We got some proteins which were downregulated, and we have localized those proteins in spermatozoa, in hamsters, even in rat and mouse. And so this is the 2D electrophoresis image. Just I'll show you just fluorescence images. So these are. So you can look into these images, and you can see hamster sperms, and you can see the GRP protein which is localized here on the head of the spermatozoa, and also in the tail, not in the middle piece of spermatozoa, but in the tail portion of the spermatozoa. So your topic was on fluorescence microscopy, so it actually stimulated me to show some of the images of spermatozoa from hamster, from mouse, and from rat. And also we used human spermatozoa to localize those proteins, that is GRP75 and ERP57. So these are the images, and this work was done in 2009. So I was there in CCMB in 2007 to 9, 2 years. So there I used this fluorescence microscopy. Dr. Saravanan, thank you so much for permitting me.
Yeah, thanks.
Thank you so much, sir.
Maybe now you can repeat it with the new techniques. Maybe you will see much better that.
Yes. It is far behind. It was in 2010, so I may repeat it again.
Yeah, definitely. It should be repeated after 7 years.
Yes. There is much advancement in the microscopy. Thank you so much, Dr. Saravanan. And Dr. Kalse, sir, you can please continue for the concluding remarks.
Thank you very much, sir. It's a nice and elaborative talk given by the distinguished speaker, Palani Sarji. How to learn life through the lenses. It is a very interesting talk, and they have studied regarding the yeast live cells imaging by using various fluorescent dyes. We have seen first time that cell cycle mitosis by these fluorescent techniques. It increases our curiosity in the microscopy. Initially, we know very little about the microscopy and these advanced microscopy and their curiosity, which increases by this lecture. Again, we should accept the amalgam of these different subjects, that is physics, chemistry, and the biology, which work jointly to distinguish, to learn, or to see the live things through which. Also, it is observed that initially we stain, that a vital staining we use for the different cells, just like a vital stain, that is Jonas green, we use for detection of mitochondria. But how to observe these mitochondria by using this fluorescent microscopy is a unique and fabulous technique which we'll use in future also. So I take this opportunity to congratulate the Palani sir and or the organizers and the principal of this college, which organized this national program, the workshop program. So thank you very much, sir.
Thank you very much, sir.
Thank you, sir. Yeah.
I'm happy to present vote of thanks towards our distinguished speaker, Dr. Sarvanand Palani, for his knowledgeable talk on advanced microscopy, which was a feast of new techniques in microscopy for the students like us, though I am a teacher. Thank you, sir. I'm also thankful to the session chairman for his knowledgeable discussion with the speaker and participant. Thank you, Professor Kalse, sir. Thank you once again. Now I'm turning towards the final vote of thanks. I, Dr. Yogesh Vasu, as an organizing secretary of this event, took an opportunity to pay my gratitude towards this teamwork. I'm very much thankful to Chief Patron, Honorable Bapu Sahib Deepak Bhai Patil, President PHGP Mandal Shada, who gives us an opportunity to serve you all. I thankful to patron Honorable Srimati Kamaltai Patil Sahib, Secretary PHGP Mandal Shada. I thanks to co-patron Principal Makaranbhai Patil, Coordinator PHGP Mandal, whose disciplined work continuously make us very special in academia. I'm also thankful to the principal of our college and Dean Science and Technology Faculty KBC NMU Jalgaon, Professor R.S. Patil sir, who continuously motivates us to organize such programs. Thank you, sir. I also thankful to our Vice Principal and Coordinator IQSC, Dr. M.K. Patel, sir, who continuously motivates us for such programs. I also pay my gratitude towards Vice Principal Dr. S.D. Sinkhedkar, sir. I also thank to Dr. R.M. Chaudhary, sir, Head Department of Zoology, for his kind support. I am thankful to all more than 570 participants, includes all faculties, research scholars, students, and academicians who joined from each and every corner of the country on Zoom platform as well as on YouTube Live. Thank you, all participants. I also thankful to the technical support and all our colleagues who helped us to make this event a grand success. Thank you. Thank you, one and all. Thank you once again.
I will add something here, Dr.
All the
Vasu.
participants. Yeah, sir. Yes, sir.
I have seen one message in the chat box that I request Dr. Saravanan sir, please guide for postdoc. So may I kindly be permitted, Dr. Ramanujam sir and Dr. Saravanan sir, to share your email on Telegram group? Is it okay?
Yeah, it's not a problem. I am not in Telegram, so I think there.
No, I will share your email in our Telegram group.
Yes.
So that the participants could get some information. Yes, about about postdoc and about other opportunities in the research field.
Yeah, sure.
So is it okay for you, sir?
Yes.
So I will share both of your emails in the Telegram group. And Ramanujam sir, thank you so much for cooperating us. And Dr. Saravanan sir, thank you so much for instead of your busy schedule, you could stole some time for us. And I may announce one more thing that today is Friday, and next Friday, in coming week, next Friday, we'll be organizing the workshop with different topics like handling of biological materials and precautions of maintaining museum specimens. It is especially for zoology students and zoology labs. So we'll be planning that. We have planned that, and it is already established, and we'll be presenting a workshop on next Friday. So it is the announcement for participants. And thank you once again, Dr. Kalse sir, Dr. Lohar sir, principal sir of our college, and Dr. Saravanan sir, Dr. Ramanujam sir. Thank you so much. And on behalf of our organizing committee, I will end this session. Thank you so much, all the participants. Thank you so much.